Hello and welcome to this video having a look at a 6-mark leveled response question which requires you to identify 3 alcohols of similar MR, well identical MR because they'll be structural isomers, and using an experimental plan to do so. So what's different about this one is it actually allows you to use an infrared spectrometer, so you can assume that you've got one of those as well, which is a little bit unusual for an A-level chemistry lab. So then it asks you to provide equations and a description of how you'll identify the 3 alcohols from any observations and results. And they direct you to use structural formulae, so it's worth bearing that in mind a bit later on. So taking our 3 alcohols, the first one is butan-1-ol, which is primary, and just recalling your alcohol's oxidation reactions, that's obviously going to be oxidized to an aldehyde and possibly to a carboxylic acid as well. With a secondary alcohol, such as butan-2-ol, it can only be oxidized to a ketone. And tertiary alcohols like 2-methyl-propan-2-ol don't easily oxidize at all. So out of those things, there is a chemical test for a carboxylic acid, and like any acid, it'll react with sodium carbonate, or any carbonate for that matter, to give salt, water, and carbon dioxide gas. So the fizzing will be the carbon dioxide gas being given off. So it's worth bearing that in mind too for a little bit later. So that's why I took you through a little bit of thinking first before we dived in and started constructing an answer. So as a kind of plan, there are 3 things that need to be in your answer. So in the terms of the plan to identify the alcohols, we've obviously looked at the oxidation of them. I would suggest going for reflux because that will allow the primary alcohol to go all the way to a carboxylic acid. So you can set up distillation if you're doing a different question. This time I'd set up reflux apparatus. So as you're probably also aware, the color change for acidified K2Cr2O7 goes from orange to green. So that indicates visually that an oxidation has happened. And you can run an infrared spectrum of the products of the oxidation to confirm any bonds that are present. So in my equations, I'm particularly taking care of how many O's in square brackets I've got. 2 for the full oxidation of a primary alcohol, and 1 for the full oxidation of a secondary alcohol. And I also don't forget to put in the H2O's as well. So I need to state that the tertiary alcohol won't react, and what you would see is no color change at the reflux stage. So the other 2, the primary and the secondary, will oxidize, so the color of the reaction mixture will go from orange to green. So that will not help us any further trying to identify the difference between the primary and the secondary alcohol. So I'm going to clear the page a little bit and take you through how to lay out the different parts of the answer clearly. So coming back to our plan, those are the 3 things we said we were going to do. In terms of the equations, we've already come up with those, so those can go in there like that. So we need to state that the 2-methyl-propan-2-ol will not react, so you will see no color change, and state that that's because it's a tertiary alcohol. So the butan-1-ol and butan-2-ol will oxidize, and the color of the reaction mixture will go from orange to green because they are primary and secondary alcohols respectively. So the butanoic acid produced from the full oxidation of butan-1-ol can be tested for by adding Na2CO3. The fizzing indicates the presence of an acid. So the ketone that would be made from the oxidation of butan-2-ol would not react in this way, so that helps you distinguish between the 2 of them. So just checking our section of the data sheet we would need to use when doing the spectral analysis. For the oxidation product of the primary alcohol, butanoic acid, IR spectroscopy will reveal peaks at 1630 to 1820 centimeter to the -1, which is the C double bond O, and at 3200 to 3600, which is the carboxylic acid OH bond. So we're looking at these 2 here. You can see the numbers there. So for the ketone that's made, the infrared spectroscopy will reveal the presence of the C double bond O, but not the COH. So the OH, this one here, will not exist because it'll only be the C double bond O that will be present in the molecule, not the OH as well. Okay, that takes us to the end of this run through this question. It's not the only way to do it, it's just my particular take on it. So let's have a look at the mark scheme. What kind of things would they want? So you have to ID the alcohols as primary, secondary and tertiary. You have to use reflux, followed by the use of IR to identify the different oxidation products. So stated reagents, I said acidified K2Cr2O7 will do for that, and conditions, and equations using the right number of O's using structural formulae. And then identification of the oxidation product would be the use of the infrared. So for level 1, which is 1 or 2 marks, you'd need to describe a basic method or give some supporting evidence from the infrared spectrum, and do the supporting evidence from the infrared spectrum, or details of reagents and conditions with some attempted equations. So moving it up a bit to a slightly higher level of quality, there's a basic method, and there's some supporting evidence from IR, and there's some details of reagents and conditions with equations. But you can see the way the language reads, there's still a few things missing. So a much better answer, which will get you 5 or 6 marks, would be a method for identifying the alcohols, all the supporting evidence from infrared, and correct details of reagents and conditions with the correct equations. Okay, as always, thanks for listening. Until next time, see you soon.